So this is an airplane here. Flown in one, or maybe you've just seen them fly. But even if you've seen them or been in one, do you know how they work? Is it magic?
Wingardium Leviosa.
Are there invisible fairies that hold the plane aloft?
All right, men, we've got a busy morning and lots of flights to carry.
Or is it science? Well, you can guess that the answer is indeed science.
That's ridiculous.
What?
So to discuss how an airplane flies, we first have to talk about the forces on an airplane, which push it around in all sorts of different directions. The first force acts on all of these vehicles. Really, it acts on everything. It's the weight force, which points down towards the center of Earth. Weight is equal to the mass of the airplane, m right here, times the acceleration due to gravity. Here on Earth, g is equal to 9.81 meters per second squared. Now, that's only for Earth. The acceleration due to gravity really depends on the mass of the planet that you're on. The larger the planet, the higher the gravity. So 9.81 meters per second squared here on Earth. The moon, however, it's smaller than Earth, so the acceleration due to gravity is only 1/6 that on Earth, 1.6 meters per second squared. This is why astronauts can bounce high on the moon, but not on Earth.
This isn't nearly as much fun.
Obviously, there has to be another force opposing the weight and pushing the airplane up. This force is called lift. Lift operates perpendicular to the airplane's wings, which are...
That is error number 1, as lift acts perpendicular to the flow direction or the relative wind.
Right here in this side view. Now, if these are only two forces, our aircraft will be able to go up and down, but it won't go anywhere. So we have to have a force that pushes the airplane forward, and this is called thrust. All vehicles have thrust, otherwise they wouldn't go anywhere like our airplane. On an aircraft, this thrust is produced by engines. There are two main types of engines. We have propellers, like this little guy right here, and jet engines, like our first model. Whatever the type of engines, they all work by the same principle. So if we draw a little side view of an engine here, the engines accelerate air out the back, this direction, and by Newton's third law, there's an equal and opposite reaction, and that's the thrust force, pushing the aircraft forward. This is really the same thing that happens when you blow up a balloon and you let it go. The air comes out the back and the balloon moves forward. We have a force that opposes the thrust. It's called drag. It points opposite the direction of flight.
Note the direction of flight is along the relative wind or along the flow vector.
The major type of drag is pressure drag, which is the force caused by the air smacking into the airplane.
He is neglecting a major cause of drag called induced drag, which comes from the generation of lift itself. This is a serious error.
Feel the pressure drag when you stick your hand out the window of a moving car. Honey, your hand please. When your hand is horizontal, it's aerodynamic and you really don't feel a lot of drag. But if you slowly turn your hand vertical, you can really feel the drag increasing. So these are our four forces on the airplane. Let's look at the equation for the magnitude of lift per unit wing area. We'll call that L. L equals 1/2 times rho times CL times V squared. It's that simple.
Here is another serious error where he misses the wing area, S sub W, in the equation, which is a critical mistake.
Okay, I'll tell you what each of these things mean. So rho, it's not a P, it's the Greek letter rho. Rho is the density of the air, which is a measure of the number of air molecules in a certain volume. Density of the air varies with altitude and temperature. So as you go higher up, the air is thinner, and so the density is lower. If we want to simplify things, we generally use the standard density, which is 1.2754 kilograms per meters cubed. V here is the speed of the aircraft, or how fast it's traveling. And CL is something called the coefficient of lift. It's a number that gives us some information about the shape of the aircraft's wings. These things right here. The coefficient of lift changes with the angle of attack.
Angle of what?
Aircraft can pitch up and down. And even if they're pitched up, they're still traveling in a horizontal direction like that. Now, the angle formed here by the horizontal direction of travel and the direction of the aircraft's nose is called the angle of attack. And we denote that with the Greek letter alpha. So we can make a little plot here of that. We're going to put coefficient of lift up on the y-axis and the angle of attack down on the x-axis. So as the airplane starts to pitch up, if I can get a little hand here, thank you. As the aircraft starts to pitch up, the coefficient of lift increases. This is a good thing because we have more lift. As we continue to increase, we eventually reach a point where we keep pitching up, but the lift starts decreasing. This is something called stall, and it's not a good thing. So we generally avoid trying to pitching up this much.
There's a similar equation for the drag per unit wing area, d. d equals 1/2 rho,
not CL, that really wouldn't make any sense, CD. As you can guess, it's the coefficient of drag times the velocity squared.
Once again, he makes the serious error of eliminating the frontal wing area. That is the wing area that's perpendicular to the relative wind, or to the flow. It's totally missing from this equation.
The coefficient of drag it's another number that tells us something about the wings, and it also varies with the angle of attack. So as the angle of attack increases, oh, thank you, the coefficient of drag increases as well. Thank you very much. This is because as the aircraft is pitching up, there is more wing area perpendicular to the flow. Now,
in this final error, he has once again eliminated the frontal area and is confusing drag with the coefficient of drag. The drag equation must have the frontal area in it, which is missing. The coefficient of drag varies with the angle of attack as well, but it is totally missing from his equations, and so his examples are not correct.
this reminds me of something that we talked about earlier. Exactly. This is very similar to whenever you hold your hand out the window.
Yes, and it exists. This is exactly the term that is missing from his equation, the frontal drag area that increases, just like holding your hand out the window of a car, but it's missing from his equation.
Window of a car. And so that's pretty much everything you need to know about how an aircraft flies. So the next time you're on an airplane or you just see one, you can really know exactly what it is that's keeping it up in the air. Nope. No, it's not them either. There you go. Now you got it.
I contacted the Khan Academy about these errors, and they fixed them by saying at the start of the lift and drag sequences, lift per unit area and drag per unit area. You can notice the change in the voice file when that occurs. But still, there's, I think, serious misconceptions that are conveyed by this video, and I hope that, that you have them straight in your own mind. Thank you.